Hi, today I want to share with you a little bit about my block detector card. So I'm going to do it in a couple different sessions. I'm going to do it with this opening in session, then I'm going to switch to a video where where you can see me actually manipulating the card, and then I'll come back onto the computer again here and we'll go through the schematic drawing and talk a little bit about EZDA, which is the program that I developed all this stuff in. So let me close up the intro, get set up, and start the um, overview. Thank you very much. Okay, to get things started, I brought one of my decoder. I keep wanting to say decoder, guys. I'm sorry. If I do it, I apologize. One of my block detector boards that I've made. Brought it up here close to the camera where you can see what's going on. The most important thing that you need to know about this is this red wire. The red wire comes into the current transformer. So you pass the wire through the current transformer, wrap it around the top, and pass it back through again. That's the secondary winding now of that current transformer. I should say primary winding. My mistake. The next thing to know is these three terminal strips here. And they're labeled. Might be a little hard to see on the camera there. I can't get it focused that close. But this one is ground. This one is VCC, or 12 volts. And this one is labeled signal. Signal is the one that goes to the computer. Also on the board, there's the sensitivity adjustment pot. You turn that with a little screwdriver, and you can adjust this card to be as sensitive as you want. The only active component on this card is a transistor right here. And we'll get into how all that works a little bit when I go over the schematic. But I'm not going to make you an expert at it. I just want you to kind of see it on paper. You'll understand what's going on a little better. With that said, let's move down here to the one I've got hooked up. So the first thing you can see, just barely off here to the corner, this is my lens system. It's my DCC and my booster combined into one package. So my output comes here for my rail power, comes out here on these two black wires. One black wire goes directly to my track jumper. The other black wire comes out through the green jumper lead, back up and into one side of the red wire, loops through the transformer, comes out the red wire to the white jumper, which comes back around and connects to the other lead to my test track. So I have a complete circuit there, and I have track power turned on. Now I'm going to use JMRI to control that track power, and I'm going to turn the track power on, and you'll hear my engine come to life. There it is. So my engine's come to life, and you can see that I have a live circuit. Now I want to turn the track power off for a second to get rid of the noise, and I want to bring my voltmeter up. Now with the power off, you can see that my signal coming out going to the computer is 5 volts. Okay, let me show you how I've got that hooked up. So coming off the signal wire, the yellow wire, goes to one lead of my voltmeter. The other lead of my voltmeter comes up and connects to ground. So my voltmeter is between ground and signal. So with power off, that would be the same as nothing on the rail because no current is being drawn. So with power off, I get 5 volts from my signal to the computer. The computer would interpret that as nothing is present. Now I'm going to turn on track voltage. As soon as I do, you see my voltage drops way down. I'm down to 0.2, 0.1 volts. If you look close, you can see that decimal point there in front of everything. Now I'm reading 0.113 to 119 volts, almost a perfect zero. When you see that, when the computer sees that, it knows that something is drawing current on the rail. So we interpret that as occupied. So again, let me turn off track voltage. And you see I jump right back up to 5 volts. If I turn on track voltage, I drop immediately to 1.4. Get a little fluctuation, but it's well below the threshold for the computer to see 0 volts. So now you can see that I'm controlling that with the power on-off switch. I'll set my JMRI controller aside, and now I'm actually going to pick the train up off the rail. And it has the same effect. So there's nothing on the rail, but there's still power applied. And my voltage went up to 5 volts. Let's see how lucky I can be about setting this back down on the rail. I did pretty good. As soon as I put it on the rail, see I dropped down to 0.1, 0.3 volts, well below the threshold for the computer to see a 0 volt signal. So with that said, let's turn this off, and I'll turn around here and get up on the computer where you can see my pretty face. Alright, now that we've kind of watched me demonstrate how the block detector card works, and you've seen it in action on the voltmeter, I'm going to go over a little bit about the EZDeck program, EZDeck EDA. This is the program that I've developed in, and I just wanted to share a little bit with you because I'm actually going to put links to all my computer cards, all the software, all the hardware, and where to get the parts and how to get the boards made. I'm not going to do that on this video. I'll do that on my card overview video. But I'm going to take time here to go over a little bit with this block detector card, because it's a simple one, a quick one, and I won't have to bore you all day with the long drawn out process. So with that said, I went to EZDeck.com, downloaded the desktop app, and installed it. You know, it's typical install, except all the defaults, and it puts the icon on your desktop. Double click it, and here's what you come up with. And of course, once you established your account and do anything, over here on the left hand side you'll see your login name. When you open it up, you'll see everything that you've been working on. So I'll go down here, let me find the block detector card, and I'll open up that project. And I have 2 files under my block detector card. One is the schematic diagram, and the other is the printed circuit board layout. So let's open up the schematic diagram here. Let you see what it looks like. Now I'm going to enlarge this a little bit, make it easier to see. These are your tools for working. Right, these are for the electrical connections, and these are for placing text and putting squares and drawing lines and doing different things like that on the diagram. So I'm going to just click these and close them up a little bit, move them up out of our way so that they don't bother us. And what I'm doing is I'm using my mouse to scroll wheel button to scroll up and down and enlarge the drawing, and then right clicking and holding it down to dragging it around, positioning it. Okay, it's pretty much like a lot of other drawing programs. So here you can see my schematic diagram, and we'll start over here on the left hand side. L1, this is the coil. This is the current transformer that we wrapped the red wire through. Okay, so you can see this is 1/2 of a transformer, and when we wrap that red wire around that, we make the other half of the transformer. coming in. Remember the little blue pot that I showed you that we adjusted for sensitivity? That's across the coil, and that either increases or decreases the sensitivity of that coil. D1, 2, and 3 chop up that signal, start converting it to a DC value for us, and then that value is put onto the base of this transistor. Now we're going to stop right there. That's kind of the input side of the card, and we're going to talk a little bit about how we power up this card. Our three terminal board that you saw on the card is over here. Number 1 was BCC, or our 12 volts DC. Number 3 was ground. So let's follow those around a little bit. You can see number 3 is common to almost every device on the board. That's another reason it's also referred to as common, as well as ground. Now up to terminal 1, we'll follow that 12 volts in. The D5 is a blocking resistor. Okay. 1.8 R4 is a current limiting resistor. And at this junction, we create a parallel branch. R3, of course, is going down to the collector of the transistor, and the other branch is going out to ZD1. ZD stands for Zener Diode, and you can see the symbol is slightly different from a regular diode. See, a regular diode has the flat cathode line, where a Zener has a crooked zigzag cathode line. And you install a Zener diode with reverse biasing, and when you do that, the Zener is designed to break down when you exceed its voltage. And ZD1 is rated, let me highlight it over here on the right hand column. You can see the information about it. It's an IN4734A_CA. Okay, and we'll talk more about this area later, but I just wanted you to see where all the information is going to be about this diode. So back over here, the diode is designed to limit the voltage to 5.1 volts because we want a 5-volt circuit, but we're applying 12 volts. So the 12 volts comes into this junction, and the diode breaks down and offers just enough resistance that this connection right here is held at 5.1 volts. So the transistor only sees 5.1 volts instead of 12 volts. So we've set up the voltage circuit here, the supply side for this transistor. We've applied ground to its emitter, and we've seen the input circuit coming into its base. Now we're using this transistor as a switch, so it's going to act just like an on-off switch, like a light circuit. And what we're doing with this transistor is called saturation. We're going to put enough voltage on its base that it's going to saturate and turn completely on. And it's just like the contacts of a switch then. It's just closed and passes this ground through the base and up to the collector. And when we do that, we're doing a switching operation. So let's see how this is accomplished. First, we'll start over here with L1 with no current flowing through the transformer. When there's no current through the transformer, there's no voltage developed on the base. So that transistor is turned off. So there's no connection between the emitter and the collector because the base is turned off. So the voltage that's coming in, and at 12 volts coming in, at this point the Zener is breaking it down, converting it to 5.1 volts. That 5.1 volts is felt to the top of the collector and out on terminal 2. And that's why the voltmeter saw 5 volts. I know you were seeing 5.5 volts. you got to give and take a little bit on all these electronics there. Everything has a plus and minus accuracy. So 5.5 volts is well within accepted norms. So we got our 5 volts there when nothing is applied, when no current is flowing through the transformer. So now let's see what happens. Then we'll go back over to L1 and we'll put the train on the rail and apply power. And of course now we see DC signal flowing to the circuits, and L1 produces a current. And that current again is modified and rectified a little bit here in D2, D3, and is placed onto the base. That 5 volts, or that voltage, I've never measured it, so I can't tell you what it is, but that voltage is enough to switch transistor Q1 to the on state. As soon as we do that, then this ground is taken into the base, passed through the base to the collector. So current flows through that transistor and up through R3 and R4 and out to our power supply. With this happening, this connection goes from a positive 5 volts to 0 volts because all the voltage is being consumed across R3. Q1 is acting just like a short circuit. So it's just like having a wire from here all the way to here. And you can see then that the ground is transferred up to this point. And so 0 volts is passed out on terminal 2 now. So we see the low voltage or no voltage going out to our computer. Yeah, you saw anything from 0.1 to 0.3 volts floating out here. That's because, again, of the tolerances on all these components. So the transistor may not get completely saturated and may consume a little bit of voltage itself, leaving a fraction of a voltage right here at this junction being felt out on terminal 2. But it's well below what the computer will interpret as an off state as opposed to an on state. So quickly you can see that's how this is all done. Very simple circuit, pretty straightforward. I didn't go into a lot of detail about all the components, but that's enough to give you a working understanding of how a decoder card works. There are, of course, other designs than this too, but they all work on the same basic function. So let me interrupt this video at this point and tell you this is a good natural point to stop and terminate the video if you were only interested in how this block detector card worked. But if you're interested in developing your own circuit cards, you might want to stay on and continue watching as I go through EZDeck and give you an overview. It's not a perfect or complete overview, but it gives you the basic idea of how to get along and develop things in the program. If you have any experience with any other type of drawing program, you know you have to go select your components, drag and drop them in, and connect them all together and stuff like that. So I didn't go into that much detail about how to drag and drop components in. They have help files as well. I just wanted to give you an overview. So it's your choice. Continue on and learn about how to make the printed circuit board, or end it now and just understand how the printed circuit board works. Thank you. So now let's take a look at how I developed the board. And we'll go in here and we'll call up a board that I've already developed. What I do is I go here on the schematic and I go up here on this symbol and I say convert to a printed circuit board. When I do that, you get the equivalent of the little spinning icon for your mouse that says I'm busy working, I'm thinking about it, let me convert all this stuff for you, and boom, you get parts and components. It's not all hooked up real nice like this. You have to do all that work yourself. But all these symbols are laid out and scattered all around on the layout. And you organize them, and then you draw the lines between them to make the connections. And you do that. See, here's our PC tools. This is, if you want to lay a wire trace or a wire track onto the board, you use this, and then you click this point, you drag it over, and you click this point, and it connects them for you. Okay? There's some places where you need to use the top of the board and the bottom of the board. This is where your layer and objects comes into play. See here, the red is for the top layer, and the blue is for the bottom layer. So go back down here now and look at our board, and the red wires show up real nice and bright. See the dull blue wires in here? That means those connections are on the bottom of the board. Sometimes wires conflict with each other. And of course, if you run a red wire on top of another red wire, it thinks it's going to make an electrical connection. So it won't let you do that unless it's at a termination point. So to avoid that, you have to use our little via connections. And you drop a little via. Let me enlarge this a little bit, make it easier to see. This is a via point right here. And I drop another via point in here. So I draw this wire first in red. Then I discover I need a red wire going here. Well, the two red wires can't cross each other. So on the red wire, I drop in a via point. I drop in another via point. I highlight the connection, the portion between the two via points, and I go over here on my layer and I tell it move it from the top layer to the bottom layer, and boom, that tells the manufacturer to put that copper strip on the bottom side and not the top. Now I can come in here and I can run this red wire from here to here. So just an overview of kind of how this is all done. Now that I have a working and designed layout, of course the purple line is the size of the board itself that I want, okay? And I can shape it and everything. My next version, I'll extend this board out a little bit more on each side so that I can put a mounting hole on each side. This time I made it too tight. I had no room for a mounting hole. I forgot about it, to be honest. But anyway, once I have my layout all worked out, then I go over here and in my design manager and I do some testing. Here it tells me how many components I have, 13. And I can refresh that right here. It tells me all my connections. And I can click on it and it points that device out for me so I can find it. Okay. Next I have what's called nets. You see I have 8 of 8 connections. Refresh and I still have 8 of 8 connections. What this does is it tests to see if I forgot to connect a wire connection somewhere. If it is, then it puts a little broken arrow symbol here instead of a check mark. Okay, this tells me all my wire connections. So if I highlight this, see it takes me to the junction between D3 and D2. Okay, so D2, it says D2 underscore 1 because D2 has 2 connections, terminal 1 or side 1 and side 2. Okay, so I'm on the D2 1 and it shows me where it's supposed to go. D2 1, D2 1. Okay, so it knows to draw that line in, or I know to draw that line in there. Once I've done that, I also do my drawing
corrections, check for errors. My drawing rules corrections, and I refresh it, I have no errors. If I had an error, then it would drop down and show me where that error was at, similar to what I've been doing with all the others. It would list them here. And the type of errors you could have is perhaps you've got items drawn too close together and there's really not enough clearance on the board for those items. Like if this terminal was too close to this one, then I would get an error here, and down here it would tell me clearance, not enough clearance, right? And then I would know to go up here and rearrange this board and check out my clearance, right? Once I've done all that, then I'm ready to actually have this card produced. And there's two things, of course, that I need to do to produce this card. So first we'll go back to the schematic diagram, okay, and BOM, which is the abbreviation for bill of materials. So I have to know what components I need to build this. So I click on bill of materials, and it generates a list of everything that I've used on that card. Okay, so it gives me the name, the designator, okay, the manufacturer's part number, the supplier. Now LCSC is, you might say, a subsidy of EZDeck, at least a committed partner, right? And so these two programs are integrated, and it expects you to buy the parts from them. You don't have to, but it makes it very convenient, very easy to do that. And you can put the order in, and it will jump out of this program and bring up LCSC, and you log in, and it creates the in basket. You double check it, you place the order, and the parts are, of course, pay, and the parts are shipped to you. Occasionally there's a part that can't be found. If it can't be found, then you order it from some other supplier. I've had a couple of those. So you look it up. I use Newark when I have problems finding it here. If you don't want to buy from them, you say export the bill of material, and it creates a comma separated variable file, which then you can open in Excel or any other spreadsheet, and it generates all this material for you. You can go hunt and find it yourself if you think you can find a better deal. So that's how you get your parts. So I'm going to cancel that, and I'm going to go back over again to my printed circuit board layout, and I'm going to go up here to generate what's called the Gerber file. Okay, when I do that, when I click that, it said, would you like to do your design rule checking before generating the Gerber files? Well, that's the same thing we did over here, design rule checking, and we checked for errors. But if you haven't done so, it's a good idea to say, yes, I want to do that, and it will check your errors for you. If you're confident, you can say, no, I just want the file. Okay, so I'm going to click yes just so you can see what it does. Okay, boom, it checked it and it passed it, and so now it says this is what your board's going to look like. Okay, you can view the Gerber file, which won't mean much to you. Okay, but it tells you now this is a 2-layer board, and this is the dimension of the card, and how many would you like to buy, and you adjust how many you want to get. The more the merrier. As always, the price goes down. This is the thickness of the board. You can choose the thickness. This is default, which is what I get. The color of the card, you can choose whatever color you want. Okay, I kind of like the blue. Surface finish, I use the default because it's the cheapest. Okay, copper weight, default 1 ounce. always been good enough for me. Okay, the manufacturer is JLC printed circuit board. Again, this is either a subsidy or a parent partner relationship between EZDA and this printed circuit board manufacturer. So if you submit this order is going to go to them, and they're going to manufacture it for you, and it gives you the price. All right, to get 10 of these cards, it's going to cost me $5. That's pretty good, right? That's, what is that? 50 cents a board. Estimated time of delivery 3 to 7 days, and they're pretty good at meeting that time. I've not had to wait long periods to get these boards in. So now if I say place the order, it jumps me out. Okay, order data generated. Please click OK to continue. Wait for everything to catch up with us. And there we go. Okay, and again, now you're in if you look up here, you're in JLC PCB. You're about to place your order. And you review your order, and again, you get to choose the colors that you want. So I'll choose blue. You see the color changes and updates, so you can kind of preview it. Everything else I'm going to leave the same. Quantity, I'll leave it 10. Over here you can see all the calculations. Okay, calculated price $5. Shipping estimate $6.19 via the Economy Express. Okay, you can change these this shipping option when you get into the ordering process, and you would save it to the cart, and then you would go to your cart and you'd review it again and pay for it, and lo and behold, they tell you, hey, we accept your order. Pretty soon you'll get an email that says, we checked your card, looks good, going into production, and then you start tracing it from there. By the end of the day, it's usually finished production. By the next day, they tell you, oh, it's shipping, and then you're waiting for it to arrive. So I'm not going to follow that through. You've ordered online, you've seen that process. It's pretty similar to everybody else's process. So I'm just canceling out of that. You can generate this and export it, right? And this is what I've done. I've generated this file and saved it down to my computer, and I post these files onto GitHub so that they're open to the public so everybody can share it. So I saved the Gerber file. So if you want to, you can just send this Gerber file straight to JCL printed circuit board, and they'll generate that card, and you don't even have to bother with any of this other stuff. Okay, but perhaps you want to play with this. You like my card, but you want the mounting holes that I forgot. Also, in that case, out here on the project, right, under Files, I can export, and I export it to an EZDA file as an EZDA file. And when I do that, okay, it saves it, block detector board, and it saves it as a JSON file. Now, a lot of you guys won't know what that is. It's a type of file that can be imported to an XML file, and you can go in and you can actually see and read it because it's all in text. But just know it's a file that EZDA can use. Okay, so I saved that file up to GitHub as well. Now, if you download that file from GitHub, then you can come here and you can say File Import, and you can select the type file, and you can import it directly. And then you can manipulate it, save it as your own project, and build the modified card. So I provide all that on GitHub. We'll get more into that later. So basically, that's the meat of everything that I've had to do to generate these cards. I hope you find this enjoyable, meaningful, a good introduction. Sometime you might want to do it yourself. And with that, I'm going to close everything up and call it a day. So have a good day. Stay safe.